First of all, I would like to thank the organizers, Hai and Shi, for the kind invitation. It's my great pleasure to be here. Yeah, it's unfortunate due to the time difference, I was not able to attend the morning's talks. Okay, so I'll talk about a recent result that I've done with Kunlun Qi and Tong Yang, both from City University of Hong Kong, on the stability and the convergence proof of the Fourier spectral method for the Boltzmann equation. I apologize for the long title, but I hope as the talk goes on, this will become clear. Okay, here's the brief outline of my talk. I'll start describing the Boltzmann equation. I guess for this audience, I really don't have to spend too much time on it, but I'll do a little bit introduction on that and to fix the notation. And then I'll mainly focus on the numerical approximation of the Boltzmann equation and discuss, introduce the Fourier-Galerkin spectral method for the Boltzmann equation. And then the main part of this talk is to discuss our new result on the stability and the convergence of this method. And finally, the conclusion. All right, so here, as everybody knows, here's the how the Boltzmann equation looks like. It's kinetic equation where the unknown is one particle probability density function. So F depends on time t, position x, and the velocity v. So F dx dv gives the probability of finding this fixed particle at time t, position x, and velocity v in the phase space. So the left-hand side of the equation is nothing but transport. So we don't have forcing term typically in Boltzmann equation. And then the right-hand side is the collision operator. So it's a we'll see in a second. This is a nonlinear integral operator that models the binary collisions among particles. So this equation should be imposed in the 6-dimensional phase space, but in mathematical term, we could also consider, say a D-dimensional space where both x and v belongs to D, where D is 1-dimensional, 2-dimensional, or 3-dimensional. But in velocity, it has to be at least 2-dimensional. Okay, and here is how the Boltzmann collision operator looks like. Again, I assume everybody is relatively familiar with this, but allow me to go through this and also with introduce some notations I use. So here we see v star, v prime, and v star prime. And these are the velocity pairs before and after a collision. So during the collision, we want to maintain the conservation of mass, momentum, and energy. Since conservation of mass is automatically conserved, and then we have these constraints for momentum and energy conservation. Then given v and v star, they can determine the outgoing. We can determine the outgoing velocities v prime and v star prime using these rules. And there are 2 degrees of freedom, which can be denoted by sigma. Sigma is a unit vector that varies along the sphere. So it's a vector along the unit sphere, as shown in this figure. So v and v star determine this big sphere. And then given a fixed direction sigma that fixed outgoing velocities, one pair of fixed of outgoing velocities. And then also in this operator, we have this B, which is the so-called collision kernel. It actually encodes the interaction mechanism or interaction potential between particles. It can be shown that this kernel only depends on the magnitude of the relative velocity and also a cosine of the deviation angle, or the scattering angle. And for numerical purpose, one can usually neglect the angular dependence by considering, say, the so-called variable Hessenfeld model, where this kernel only depends on the relative velocity raised to some power. And some particular cases are, say, lambda equal to 1, we get the Hessenfeld model, and lambda equal to 0, it gives you the maximum molecule. So then in this operator, we have the gain term, which is a positive part, and we have the loss term, right? So for fixed V, we want to integrate for all possible V star and sigma. And the loss term just means that when particles collide, they make less of particles with velocity v, right? So this why this is a minus term, and for the gain term, it means because the collisions are reversible, so when particles collide with velocities v prime and v star prime, they will generate or produce particles with velocity v. So that's why this is contribute to a positive term. Okay, and some properties of collision operator, as is well known, the operator conserves mass, momentum, and energy. So which means if you multiply by Q by 1 V and V square and integrate with respect to V, we always get 0. And also we have this well-known Boltzmann's H-theorem, which is that the entropy of the system is always increasing. Physical entropy is always increasing, and this equality sign is obtained if and only if the collision operator is 0, and which also means F reaches the local equilibrium. So this F takes the form of the Maxwell-Boltzmann distribution, where this rho is the density, U is the bulk velocity, T is the temperature. These are the quantities determined by the moments of F. Okay, so my main focus here is to see how can we numerically solve the Boltzmann equation. And obviously, to solve this equation, the main difficulty comes from the collision operator, right? Just to take a closer look, we see this is a relatively high-dimensional integral operator. In the physically relevant three-dimensional case, the right-hand side, this is a 5-fold integral. And its operator, so you have to evaluate it at every velocity point, right? And if you're solving the full Boltzmann equation, we have also to compute it at every spatial point and every time step. So this is very expensive. And also, this is a nonlinear operator, right? To be precise, it's a quadratic operator. So for linear operators, generally, we have many fast solvers. By doing a fast matrix vector multiplication, we can do this relatively efficiently. But for nonlinear operators, there's no generic method. And also, because at the continuous level, the Boltzmann operator has many nice physical properties like conservation, entropy, positivity, so on and so forth. And when we do the numerical approximation, we want to preserve these properties as much as we can. And with that being said, the general strategy to solve the Boltzmann equation has been mainly split into two categories. The first one is the probabilistic method. It's well known, and the direct simulation Monte Carlo method, and still widely used today for I would say high dimensional like 3D simulations, because it's an efficient method and it's very easy to implement. But on the other hand, it also suffers from, the noise, right, with low convergence and random fluctuations. And for the past 20 years also, the deterministic method for solving the Boltzmann equation has become very popular, partly due to the computing, the increase of the computing power. And among the deterministic approach, I would say there are mainly two popular categories of methods. And the first one is the so-called discrete velocity method or discrete velocity model. although originally this method are used really to introduce to really to study the kinetic equation, not really for numerical purpose, but they can be used as a numerical method as well. Because idea is very simple. You just introduce some discrete velocity points in the velocity domain, and then introduce a proper quadrature to discretize the collision integral. And if you do that properly, in fact, you can maintain the physical properties of the operator. Namely, you can get the positivity, conservation, and even the entropy decay. So this is very nice. But on the other hand, since this is just like doing a direct, approximation, right, of the integral by quadrature, and the cost associated to that is very high. And also the convergence of this method. So this method indeed converge, but the accuracy is quite low, generally speaking. And another method that gets popularized in the past few years is the spectral method, in particular the Fourier-based spectral method, because there are a class of spectral methods, so can offer a very high accuracy for the approximation, and they are still expensive, relatively expensive, and also there are ways to further accelerate this method. So in the end, you obtain a relatively good efficiency and accuracy trade-off. But the downside of this method, I should say, if you are really looking at preserving the physical structures, they cannot. They can approximate these properties with a spectral accuracy, but they don't strictly preserve that. In fact, this also, I will also bring back to this, get back to this issue in the following. Okay, but then so again, due to its high accuracy, and this is the method we want to pursue. And this method was introduced in the 2000s by Lorenzo Preschi and Giovanni Russo. So here, just to lay out the basis, let me introduce this method briefly. So from this point on, I will focus on the spatially homogeneous Boltzmann equation. Namely, I take out the transport part, the convection part, but just considering the Boltzmann equation in the velocity space. And the velocity dimension, as I mentioned before, could be actually at least two-dimensional, because in 1D Boltzmann equation doesn't make sense. So either 2 or 3 dimension. And it's the initial value problem. And in order to apply the Fourier spectral method, the first thing we do is we have to truncate our domain, because we cannot deal with a bounded domain. So we truncate the domain from RD to a torus to a cubic domain, say from negative L to L. And then we also need to do a change of variable in the collision operator. So remember the original form, there is integration in V star. But now we don't do that. We actually do instead do the integration with respect to the relative velocity, which is called Q here. But it's completely equivalent, right, before truncation. So we do a change of variable now to integrate in Q. And then I have to also to truncate my integral, right? Since my domain is already, computational domain is already truncated, and the integral bounds cannot be unbounded. Otherwise, you are integrating an infinite object. So then what we do is, what one can do is to truncate this Q to a ball, BR. So it's a ball centered at origin with radius R. And then, I'll also use the following notation. So for this vector Q, I use the absolute value to denote its magnitude, and this Q hat to denote its direction. And then the kernel, in fact, only depends on the inner product of sigma and the Q hat, right? Once we have this preparation, then what we do is we approximate F by a truncated Fourier series that everybody knows. So I approximate F by Fn using this form. Again, here I abuse notation a bit. So note that this K should be really a multi-dimensional vector, right? When saying k from negative n/2 to n/2, I really means that each component of k belongs to this range. Okay, and we introduce these answers for my solution F. The next thing to do is it's a standard in any spectral method, a Galerkin-based spectral method. So we substitute this Fn into my Boltzmann equation here, and then project it. So I'll impose the residual of that equation to be orthogonal to this space Pn, right? It's a Galerkin projection. So in the end, we get a system of ODEs, which each one advance the case mode of my numerical solution, right? And the initial condition is projected as well. And what is complicated is, of course, the projection of the collision operator. So after a little bit work, you will see the case mode of the collision operator can be written as follows. So you see this is a big summation, but it's actually a constrained summation. So L plus M is equal to K. So this partly reflects the convolutional structure in the collision integral. And then we have this weight. So this G is a big matrix, right? It depends on two indices, L and M. And it's written this way, and you see this complex exponential. This is due to the fact that we are using the Fourier basis. And the nice thing about it is you can also clearly see the gain part and loss part of the collision operator. So those translate to G as follows. So both the gain and loss term can be represented uniformly using this G, right? Because for the gain term, if you pick L to be equal to M, you recover the loss term. Okay, then in the end, what we do, I mean, what the direct Fourier spectral method does is the following steps. So once again, look at this big sum. You see this G, this weight matrix. It has nothing to do with the function f, right? With your solution, which means you can pre-compute it and store it somewhere and use it later. And so this step, I'll call it pre-computation, and you store it somewhere. And then in the online step or stage, what we do is we first prepare the initial data. And this is easy, you just do just do this for approximation. And then at each time step, we solve this ODE system. But in order to do that, we have to evaluate this QK. And this QK, although it looks like a convolution, but it's not really, right? It's a weighted convolution. So one has to do that directly. So evaluate this sum. Once we get QK, we do time stepping to obtain FK at new time step. So it's fairly straightforward. And repeat until the final time, right? But there are two issues here, like I highlighted in red. First of all, you have to do the pre-computation, and you can wait long enough to get this. But the thing is, the storage requirement is really demanding because this is like a 6-dimensional matrix, right, in 3D. So to store this matrix, it takes the memory like n to the power 2D. So you cannot really take a too big n. And then in the online stage, to evaluate this QK by doing this sum, right? The sum, the computational cost will be quadratic as well. So this can also be expensive when dimension is high and when n is big. So this is not the focus of this talk, but just for your information, I want to mention that in the past few years, we have introduced fast algorithms to accelerate the direct Fourier spectrum method. So initial work is in this 2017 paper, where we introduce a fast strategy to speed up this method, as well as to elevate its memory constraint in the pre-computation stage. And for your curiosity, the idea is very simple. Basically, we don't pre-compute this whole matrix, this giant matrix G, but rather we move some of the online computation part of it, offline computation, to online by using quadratures. And when we do that, in fact, you render the weighted convolution, so this big sum here, into a few pure convolutions, so that you can evaluate that using FFT. So in the end, both the computational complexity and also the storage requirement can be reduced. And this idea turns out to be quite generic. It has been generalized to various cases. For example, the multi-species Boltzmann equation, and also inelastic Boltzmann equation, and recently we also use it to treat the non-cutoff Boltzmann equation. So it's not necessarily limited to the original, single species case. All right, and now I want to get back to setback to discuss a little bit the theoretical properties of this method. So we have a spectral method for the Boltzmann equation, and it achieves good accuracy and efficiency trade-off. And numerous examples have shown that they work pretty well in practice. But now the question is, can we say something about its stability and convergence? Right. There are some, regarding this, there are some good news and bad news. So the difficulties here is, as we can see, the equation is nonlinear, right? Generally, to do the nonlinear analysis is harder than the linear case, and also the key challenge here is, if we want to establish the stability of the Fourier spectrum method, the first thing you lose by using this method is you don't have the positivity of the solution. Right, because when we do the truncated Fourier approximation, one does not necessarily preserve the positivity of the reconstructed solution Fn. But the positivity is the key to many stability estimates of the kinetic equation or Boltzmann equation, as we all know, right? It can be easily seen by this simple equation. If we check the L1 norm of the solution, and if F is positive, then this is just equal to this, and plus we also have the mass conservation. This already lead me to to the L1 norm of the initial condition. So we already have some sort of L1 stability, but now we don't have this anymore. But there are also some good news. The method, although it does not preserve the positivity, it does preserve the mass, right? Because this constant 1 lies in the Fourier expansion space. So at least we have one conservation here, and also the domain is bounded. So many difficulties, in analysis of kinetic equation, of course, is due to the unbounded domain. And here we sort of, easy our life, right, to consider a bounded domain. Okay. And now, before I go into details, just to give you some idea of what has been done already. We are certainly not the first to consider this problem, and in the past there are two works discussing the stability of the Fourier spectral method. The first one dates back to 2000, again by Presky and Russo. Where they propose to apply a positivity preserving filter to the equation or to the numerical method to enforce the positivity of the solution. But once you have the positivity, you can use the techniques for the continuous equation to get the stability. So very easily. But I should say that the motivation of using spectral method is to get a high accuracy. But once you apply the filter, usually this will introduce a lot of smearing so that you no longer have the spectral accuracy. So depending on the filter you use, but generally speaking, your accuracy immediately drop down to first or second order accuracy. So this is not, I mean, the desired way to do it, right? Maybe theoretically this as a way to obtain a stability, but in practice, we never apply this kind of filter unless, say, we have a discontinuity, we have Gibbs phenomenon, we want to suppress that, we apply filter. And more recently, there's a great work by Francis Faber and Clement Monod, where they did actually a very systematic study of the Fourier spectral method, and they show that without using any filter, I think the Fourier spectral method is stable. And the key in their proof is to use a spreading or mixing property of the gain term of the collision operator, and to show that the solution, even though originally it may be negative somewhere, after some time, it will become everywhere positive. Once you restore the positivity, and since you also have the conservation of mass, so then everything is fine. So the stability can be obtained. So then, provided there are these two great works, why we are interested in a new way, right? So here we want to give a new proof. I mean, for the stability of this method, the approach we take is different. We want to estimate the L2 norm of the negative part of the solution and show that it can be controlled. And this means that we don't really require the solution to be positive everywhere in order for the method to remain stable, because it's only the L2 norm is bounded. And also the proof, we think our proof is relatively easier because it does not rely on this spreading or mixing property of the gain term. It's somehow easier, at least in my opinion. Okay, so I guess I'll quickly explain what we do. The idea is very simple. So in order to do that, first of all, let me formulate my problem in this way. So this left-hand side is the original Boltzmann equation after truncation. Okay, and then the right-hand side is the equation after the Fourier-Galerkin spectral approximation. Here, I use this P curly P to denote, I mean, the projection operator onto the space Pn. Okay, it's the space of the trigonometric polynomial space of degree up to n. And then for the initial condition, we just project the initial data. And here I have to impose some assumptions. The big assumption we use here, of course, this is a cutoff case. So we assume the collision kernel has this form where lambda is between 0 and 1, and the angular part is integral. So it's a cutoff kernel, simplest case. And then for the initial condition, we require to at least belong to L1 and H1. So this H1 is important. We need at least H1 to obtain this result. And we assume this initial condition is periodic and not negative. But of course, after projection, this Fn may not be positive. And also for initial condition, initial data, we require the following. So for any epsilon, we can find the integer n such that when n is large enough, the L1 norm of the projected initial data is bounded by twice of L1 norm of the initial condition. And this is not a very restrictive condition, right? Because the Fourier approximation is convergent under certain condition, and this can be made possible. And the second condition is, I would say, it's a little bit restrictive, but it can be done for certain initial data. This requires that the negative part of the initial condition, right after the Fourier projection, can be made arbitrarily small. Okay, so with this assumption, here's our main result. we show that there exists an integer n naught depending only on the final time, a given arbitrary final time, and the initial condition f0, such that for all n greater than this value, n0, n naught, this numerical system has a unique solution, belongs to L1 and H1, and furthermore, it satisfies the stability estimate. So during this arbitrary time interval from 0 to capital T, the L1 norm of the numerical solution is always bounded twice of its initial condition. Okay, why this is, I mean, this result is, so let me give you, in this slide, just give you the main strategy of this proof. So essentially, our proof is based on the iteration procedure. It's split into two steps. So I want to first deal with this stability over a small time interval from 0 to tau. Okay, and to achieve that, we do the following steps. So we first choose an n such that my initial condition after projection whose L1 norm can be bounded by this. And this is in fact my assumption here, right? And this can be done. And then with this n, we establish a local wild-postness result. So we determine a small time tau such that over this short time interval, there exists a unique solution Fn, which satisfies this constraint. Right. This is a local wild-postness results, and it's we can do this using just a fixed point argument. This is not too difficult. But the thing is, you see, after this small time interval, the L1 norm of the numerical solution is expanded, right? Previously, this is 2, but now it's 4. But this is expectable because the Boltzmann equation is nonlinear. And if you just do simple bound, then this will be amplified. But now the trick is to really surprise this value and to make it back to value 2. And in order to do that, we based on this L1 bond, one can control the negative part, the L2 norm of the negative part of the solution over this interval. So this is the key estimate that one need to obtain. Now you see, so K0 and K1, these are constants depending only on the initial condition and the final time. And this is the initial negative part of the solution, which we assumed it can be made arbitrarily small. And here we have an n in the denominator, so that as long as you choose n large enough, you can make this f minus to be arbitrarily small. So this is the key. I'm not sure I have the time to do that, maybe, so let me just leave it this. And once you can control this f minus, then we can use the conservation to really control the L1 norm of the numerical solution. Because if you check the L1 norm, this is equal to, of course, to this integral, and it's equal to 2 times f minus plus fn. Then for this part, this is, I mean, L1 norm of the negative f minus. And this part, the second part, is where we use the key property of the mass conservation. So this brings you back to the initial condition. And the last inequality, again, is due to my domain is bounded. So this is easy. So L1 norm is bounded f minus, the L1 norm of f minus is bounded by L2 norm of f minus. Now you see, as long as I can make this part relative arbitrarily small, I can make this L1 norm of Fn to be less than 2 times F0. So L1 norm of the initial condition. So in this way, you see I suppress this 4 to 2. I mean, I decrease that from 4 to 2 so that I'm back to the initial configuration, right? Because initially my condition is like this. So now I'm back here. Then you can, this allow you to do the iteration procedure. So you just repeat this procedure to build your solution to tau to 2 tau and 2 tau, 3 tau, so on and so forth until you reach the final time. I don't know if I have time to say this, but maybe I'll just quickly elaborate on this key estimate, this right part, right? This really relies on the careful estimate of the gain term and loss term of the collation operator. So we first write the Fourier spectral method in the following way. I mean, this is a straightforward way of writing it, right? So I put the projection part, so to this En, and then I have Q gain and Q loss. Then we estimate each of these terms by multiplying them by essentially Fn minus. We estimate both gain and loss terms separately, and this is the key. We have to do them separately, and then use that Fn can be splitted, decomposed into this F plus and F minus, and split everything, and also use this this well-known estimate of gain and loss term of the collation operator, so that in the end we can obtain these kind of limits. And another thing we need to leverage on is the spectral approximation property. So for this En part, we know very well from the spectral approximation, the L2 norm of this projection operator can be bounded by this kind of form, right? So if we assume Fn belongs to H1, then we get N in the denominator. And this is the key, because we really need this term to control, to make this arbitrarily small. And in the end, you just multiply both hand sides by Fn minus and do the ground wall taps inequality. Then you can estimate Fn minus. Okay, so once you obtain the stability result, we can easily generalize to to establish the spectral accuracy. Here, the basic assumptions are essentially the same as before, except we raise this condition to also belong to HK, right? Because we want a higher, a faster convergence. So, and then with that, we define the error function and do the standard estimate. In the end, one can establish is as long as you choose this N large enough, we have the spectral accuracy. Namely, the numerical error is bounded by this kind of form, where the constant C only depends on the initial condition and the final time, and the denominator is n to the power k, right? Because my numerical solution, because my initial condition belongs to HK, so I can obtain a case power convergence. Okay, so with that, I guess I can conclude. So we introduce a simple, I hope looks simple, new stability and convergence proof for the Fourier-Galerkin spectral method. And this is established for the spatially homogeneous and of course the cutoff Boltzmann equation. And regarding some ongoing and future work, there are two directions that we would like to explore. The first one is, I'm talking about the original, direct Fourier spectral method, but I say that in the fast algorithm, we have to introduce some quadratures, right? So, so then a natural question to ask, can you obtain a complete stability and convergence result for the fast algorithms when you have the quadratures? And the second is a harder problem. To establish the stability in the non-cutoff case. I don't see a way of doing this at this point, because you see in the cutoff case, our estimate highly relies on the fact that we can split the gain and loss term and estimate each part carefully. But in the non-cutoff case, this is no longer possible. But it's an interesting open problem to think about. So with that, I'll stop. And if you're interested, all the papers mentioned in this talk can be found in my webpage. Thank you. Thank you for your attention.
Okay. Thank you, Jingwei. We have time for questions or comments.
Can I ask a question, please?
Sure.
Please.
Okay, can you hear me?
Yes. Hi, Tom.
Yes, at first, thank you for this very nice talk, Jingwei. I wanted to ask you, did you consider in this work the large time behavior?
The what?
Did you try, Do you have an idea to where I mean, does your method converge to the Maxwellian in large time, or in the trends to equilibrium?
Yeah, so you see, this is not a long time result.
I know. But I consider the synthetic stability then, or
we haven't.
So there's no way. Do you think with your technique there is no way to have a simpler proof than the one from Clément and Francis' paper, basically?
Probably yes, but because I have to admit, and you also know that because the long-time behavior of the first spectral method is not that great, right? Because in the end you convert to a constant Maxwellian. So I guess with some effort, it's possible to get generalize that result. But yeah, I haven't really seriously think about it.
Okay.
Yeah.
So maybe we should discuss some of this day.
Yeah, sure. Yeah.
Thank you.
Thank you.
Other questions? You can also send comments or questions by chat. So maybe I can ask something.
Sure.
You said that the conservation of the L1 norm is very important, but you are not working on the full space, and you have to choose a box minus L.
Yes.
So you have some criterion how to choose this box, or?
Yes, that's a good question. So in fact, that has been explored a lot in the past few years. And in fact, when Lorenzo, in his this original work, he already talked about how to choose this box. So inevitably, you introduce error, right, by doing this truncation. In principle, the larger the domain you use, I mean, the better accuracy you can get. But once you do a very large domain, you have to also to use a large n to compensate that. So in practice, it's really not I should not say there's a complete answer to how to choose this L and N. It's really, there are some rough criteria, which if you're interested, you can check this paper. But I should say in practice, this is really done empirically. You choose a relatively large L, say at least twice of the compact support of F, and then you do the corresponding N. And if you find that domain is not large enough, you may want to enlarge that. Yeah.
Okay.
So when I talk about the conservation of mass, I'm really talking about, so I already reduced myself to this bounded domain. So I'm talking about the conservation over that bounded domain. So does that?
Yes. Thank you very much. Thank you very much.